We want to continue to build up our language with an kind of formalism for how we talk about aqueous chemistry by talking about the idea of solubility. So the concept of solubility is the idea that when you take something and you call it a solute and try to dissolve it in a given solvent, does it actually form a solution? And soluble compounds do form a solution, and insoluble compounds do not dissolve. Whether or not a particular solute is soluble in a particular solvent depends on the choice of both compounds. There is no solvent that dissolves everything, and there is no solute that is soluble in all solvents. So solubility, we would say, is this solute soluble? So salt dissolves in water, so salt is soluble in water is kind of the language that we're looking at. So can we form a solution if we try? Along this end, when we go to do this, when we go to dissolve any compound, there's always going to be a limit to how much we can dissolve. So the question is, can you, get some to dissolve in the solution? And so if we look at, for example, salt. So if I take, say, 30 grams of salt and I put it into 100 milliliters of water, it will all dissolve. It makes a solution. This is homogeneous. We'd be able to see through it. It would still look like clear water. And so we can get all 30 grams to dissolve in there. Once you hit, if you keep going, you keep trying to say, let's push it, add some more salt. Say you try to add 40 grams of salt into your same 100 milliliters of water. Well, not all of it will dissolve. 36 of the grams do dissolve, but 4 are left over. 4 remain undissolved. So you have formed a solution. This liquid here is a homogeneous solution, but there is this tiny little bit of undissolved salt, and as a result, this whole thing would be a heterogeneous mixture because you have that liquid, but there's also a little bit of solid in there. So we call this a saturated solution. So saturated solutions have the maximum amount of a given solute in there. You've reached the maximum amount you can get dissolved in that liquid, in that solvent that you've chosen. And so it doesn't matter what you're trying to dissolve, you're always going to hit this saturation limit. So when we talk about solubility, what we're talking about is relative differences in where that saturation limit is. So for example, if you have something that is soluble, like say sodium chloride in water, 36 grams in 100 milliliters. That's 100 grams of water. You can put 36 grams of salt. That is so much in there, right? That is over a third of the mass is now can be, sodium chloride. You have 136 grams. 36 of which is sodium chloride. That is a ton that can be dissolved. Something that would be insoluble would be something like silver chloride. If you try to dissolve silver chloride in water, you can get some to dissolve. You can get, this would be 0.5 milligrams of silver chloride in 100 milliliters of water. That is such a tiny, tiny amount that it's not useful. So that idea, that graphic of where does the solid start to collect happens almost immediately, right? If you add 1 milligram of silver chloride, you'll see solid in the solution. That's not a lot of mass, and that is just it very, very quickly shows up. So you can't really create a solution of silver chloride with any sort of high concentration. The molarity would be really, really low, and it's functionally not really, it doesn't have any properties that are that different from just water. Whereas sodium chloride, you can get so much dissolved that you can really change its properties. So for example, it starts to conduct electricity because of all the silver chloride. There's not really enough silver, because of all the sodium chloride, NaCl. There's not really going to be enough silver chloride ever dissolved to drive conductivity. When it comes to predicting solubility, we said that both the solvent and the solute matter. So for our purposes, for right now, we're only going to learn how to predict the solubility of ionic compounds in water. So if you're using water as the solvent, which ionic compounds are going to be soluble in the solvent? If you want to learn about covalent compounds, got to come back for Gen Chem 2. So, but for Gen Chem 1, we're going to focus just on ionic compounds in water. And here are the rules that we can use. And we're going to work through these one at a time and do some examples using them. But these rules are a set of guidelines based on the ions contained in your compound. And it's from those ions in the compound determines whether or not it's soluble. And you'll notice the rules are numbered. They are the order of importance. So rule 1 is the first rule. You'll see group 1A compounds and ammonium compounds. If you find an ion that fits that category, you're done. It's a soluble compound. It doesn't matter what the other thing is. So you follow it until you find a rule that clicks it. Now, you can try really hard and you don't have to try that hard. There are plenty of compounds that these rules can't deal with. We really aren't too concerned with those. If you really want to get into the weeds, I'm more than happy to discuss any of that, but we're going to focus on kind of common ionic compounds, all of which would be described by this set of rules. Anything that we're going to deal with, I'm not going to give you anything that's not that you can't use these rules to describe. So let's take a look at each rule. 1. Group 1A compounds and ammonium compounds are soluble. So group 1A compounds, that is my alkali metals. So any ionic compound containing an alkali metal or ammonium, hey, that was why we learned it, is going to be soluble. So ammonium is anything that contains ammonium, and then group 1A, lithium, sodium, potassium, rubidium, cesium, right? Those ions are always going to indicate that it's a soluble compound. Again, it doesn't matter what the anion is. These things are going to be soluble. That's why, if you kind of notice in lab, we use sodium cations a lot, and we use potassium cations a lot. A lot of times, potentially the other ion, the anion in that solution, is what matters for the chemistry. The reason why sodium and potassium are there is because whenever they're in a compound, it's a soluble compound. So the anion dissolves right along with it, and you can get a soluble compound. Those are also relatively cheap as far as all the other things on this list go. 2. Nitrates, acetates, chlorates, and perchlorates are soluble. This rule is similar to rule 1, but it's just about anions. You'll note, again, it only matters what the anion is. Of these, you won't necessarily find a lot of these in the lab. Acetate has some other kind of properties. It's chemically reactive. Perchlorate is explosive. So we tend not to use those too much. But nitrate, we'll see a lot of. We use nitrate a lot. It does have some reactivity to it. We'll see it do some pretty gnarly reactivity in next week's lab. But it, for the most part, is used to, again, be very soluble. So if you have a cation you want to get dissolved, nitrates are always soluble. So if you pair that hard to dissolve cation with nitrate, its rules don't matter. Nitrate's going to go out into solution. Rule 3. Silver, lead, and mercury compounds are insoluble. So these are heavy metals. If you see silver, lead in a different form, or mercury in your compound, those are insoluble compounds. Those are always insoluble. It doesn't matter what they are paired with. Just like before, just the outcome is the opposite. We're dealing with insoluble as opposed to soluble. And you'll note these rules are in order. So if rule 1 or rule 2 has already been tripped, rule 3 doesn't matter. Rule 1 and rule 2 are more important. Chlorides, bromides, and iodides are soluble. Most of the halogens. You'll note fluoride is not on here. Fluorides don't have the similar rules. Only chlorides, bromides, and iodides here. 5. Sulfates are soluble except for calcium and barium sulfate. So you'll note they're starting to get some sulfates are all soluble. You're starting to find some exceptions. This is because we're further down the rules. They're starting to become a little less strict. These are rules that have more exceptions to them built in. They're not as strong in terms of preferences for those particular ions, whether or not to dissolve or stay in the solid undissolved. Compounds with a 2- or 3- anion are insoluble. This is a pretty big catch-all. You'll note there's a lot of ions on here. We have some monoatomic ions. We also have our polyatomic ions. Anything that you can find that has a 2- or 3- charge is going to be insoluble. You'll note again, this rule isn't in all. This rule is 6, so your other rules have to not have come into effect. So these would only take and come into account when you don't meet rules 1 through 5. So if you find one of those rules first, that rule would matter more. 7, hydroxides are insoluble except for calcium hydroxide and barium hydroxide. Again, another exception. You do want to be careful. Calcium hydroxide and barium hydroxide are the exceptions that are soluble. It is very confusing because calcium and barium sulfate are exceptions that are insoluble. So they go, it's the same atoms, but they go in opposite directions. It is confusing. And it is, a lot to keep track of. But you have these rules. You can always use these rules, and I encourage you to use them when you're working through any problems or examples. And you'll eventually kind of develop some intuition about these rules. The ones that are up top get used more frequently. And so we'll develop some intuition without needing to rely on them, but we can use them while we still have them. Along those lines, let's get some practice determining whether or not these salts are soluble in water. So I have Na3PO4, NH4-2S, CaCl2, AgCl, and AgNO3. Those are respectively sodium phosphate, ammonium sulfide, calcium chloride, silver chloride, and silver nitrate. We want to take a look at these. When we're determining whether or not salts are soluble, we can use our rules. And when we use those rules, we can go ahead and it's always going to be based around the ions. So we want to take each of these compounds, figure out what ions are contained in there, and then use our rules. So let's take a look at doing that. So when we're looking at whether or not a salt is soluble, one of the things that is we want to note, it is denoted they're salts. So these are all ionic. We could check that they're all ionic. But in this case, we're just being told, so let's not waste that information. But when we have an ionic compound and we want to figure out whether or not it's soluble, we can always use our solubility rules, right? We can use our solubility rules, and these are based around the ions contained in that ionic compound. So just like we saw, we're looking at dissolving things, figuring out what ions are in the compound, naming is figuring out what ions are in the compound. We want to use that same idea. What is in the compound? So if I have Na3PO4, we know Na is sodium, so that's going to be my cut right there. I know that means that I have Na plus, and then I have PO4, and PO4 has to be the anion. Everything else, because sodium is just a metal atom, so everything else has to be an anion. It's a polyatomic ion. This is called phosphate, and the charge is 3-. You can learn that, or you could look it up, and you can look it up. You can know to look it up when you see, hey, I got a metal atom. Everything else has to be the anion. So that's Na plus, and then PO4 3-. You will note that in the compound there are actually 3 of them. 3 sodiums. That's great. When we're talking about solubility rules, we don't actually care about the number of them. We only care about what the ions are. So we don't care that it doesn't say if you have 1 sodium atom or 2 sodium atoms. So I don't care about the number. I just want to parse out what it is. So I get Na plus PO4 3-. So when I go through my rules, I can see that rule 1 says group 1A compounds and ammonium compounds are soluble. So group 1A compounds. Okay, if I go to the periodic table, group 1A is over here. Hey, that's lithium, sodium, potassium, rubidium, cesium. That's the alkali metals that we're looking at for ionic compounds. So Na plus, that right there, that is group 1A. So that means this compound is soluble by rule 1. Okay. You will note I did not analyze phosphate. The PO4 3- doesn't matter. When I look at these rules, once I find a rule, in this case rule 1, that's true, that's just how it goes. This is a soluble compound. You can see down here, rule 6, compounds with a 2- or 3- anion, that's 3-, are insoluble. This only comes into effect if one of these rules doesn't come into play first. So in this case, because you had the sodium, rule 1 trips, you don't care about rule 6 because that has a lower priority. Rule 1 is a high priority rule. So soluble because it contains sodium. Doesn't matter about the back end. If you didn't have sodium, that phosphate would start to matter. But because you have the sodium, you trip that rule. You can see the typo I made that corrected, but NH4 to S right there. NH4 plus and S2 minus. And, you know, ammonium, again, those parentheses indicate that you are dealing with a polyatomic ion. You're probably just going to ammonium, hopefully soon. But you also can know to look up, hey, those parentheses mean it's a polyatomic. So I need to go find what NH4 is. It's NH4 plus. S is then your anion. You can figure out that S is, and this would be 0, -1, -2 to pick up the charge on your S. So if I return to my solubility rules, rule 1, group 1A compounds and ammonium compounds are soluble. So this is why ammonium is very important. It's highly soluble. And so ammonium is an important, get you on rule 1. And you can see right there, this thing is soluble. Again, by rule 1. You see that rule 1 is very important. So sodium, potassium, you know, if you're watching what we're using in lab, right, the compounds that we're using in lab, sodium and potassium sure do show up a lot in compounds, right? We use sodium and then whatever the anion is, potassium, whatever the anion is, because they are always soluble. If you want to get sulfide or phosphate dissolved, right, because both ions have to, both types of ions go out and dissolve together. And so if you want to get one of them out there, you need, if you want to get an anion dissolved, you need a cation that's going to want to dissolve. And sodium and ammonium are both really good candidates to accomplish that. All right, let's take a look at this other column then. Calcium chloride. So if we look, CaCl2, there's only 2 types of atoms. So we know that calcium is my cation and chloride is my anion. So I'd be looking at A2 plus and Cl minus. Calcium's in column 2A, chlorine is in column 7A. It's a halogen, so it goes to -1. All right, so now I want to return to my rules. Group 1A compounds and ammonium compounds. Not ammonium, calcium's in group 2A, so no. Nitrates, acetates, chlorates, and perchlorates. One of the things we can parse them at, those are all 8s, 8, 8, 8, that ATE pattern, those are all polyatomics. Okay, so those are all polyatomics. We can look up what their formula is, but importantly, that's a monoatomic, so I'm definitely not working with it. This is chloride, so we want to be careful. It's not chlorate or perchlorate. ATE, that's a polyatomic. So no on rule 2. We've got rule 3. Silver, lead, mercury. No, we just don't have that element. Those are specific elements. We don't have those elements. Rule 4. Chlorides, bromides, and iodides are soluble. We got that. This right here, we're now pulling the anion. The compound is soluble, and it's due to rule 4. There's a chloride in this compound. We didn't trigger rule 1, 2, or 3 so far. So the rule 4 is what comes into account. Chloride is there, so this thing is soluble. Next, I have silver chloride. Okay. And so silver and chloride. Reminder, silver is a transition metal. So normally we would need a number, but silver, zinc, aluminum are the exceptions. That is Ag plus. Silver is always Ag plus. Cl is always minus. You can also figure it out because you know this compound has to be neutral. Chloride is affixed because it's an anion, it's a halogen, so you could figure out that silver needs to be plus. And I didn't ask you to name it, so even if you didn't know that silver was fixed and you thought the name of this was silver 1 chloride, it doesn't matter for solubility. So you can still figure it out using the tool, the approaches that we learned previously to figure out charges. Okay, so silver chloride, I got the Ag and the chloride. So chloride was our star before. We'll see how it goes. Group 1A compounds, well, that's the alkali metals. Silver's transition. Ammonium, no, we don't have that. Nitrate, ATE. Acetate, ATE. Chlorate, ATE. Perchlorates, ATE. No, we're dealing with monoatomic chloride, not any of that stuff. Rule 3, silver, lead, and mercury compounds are insoluble. Well, looky here. I got silver. Silver makes this compound insoluble by rule 3. So you can see that chloride is rule 4. So chlorides tend to want to dissolve, but silver has a stronger preference to not dissolve. So chlorides can get most cations to dissolve, but not silver. These rules are in this order for a reason. These are the preferential rule orders for these rules. Okay, that silver chloride tends to want to be dissolved, wants to float around out in the solution, not stay in the solid, become aqueous. And calcium's happy to tag along. Silver's not. Silver is not happy to just tag along. It's not going to go out on its own. So this stays dissolved. It does not separate out into ions. It stays nice and solid. It does not form a homogeneous mixture where it dissolves. We look at silver nitrate then. We cut that. Again, Ag+, that's a metal. It has to be just a single atom. NO3 is then a polyatomic. It is nitrate. It's a very common one, worthwhile to learn. We can also look it up. That is a charge of -1. Its name is nitrate. So we have silver and nitrate. Now we have our ions. We're going to return to our rules. Group 1A compounds, no, it's silver. It's not ammonium. Nitrates, acetates, chlorides, and perchlorates. ATE, that's a polyatomic ion featuring nitrogen. This right here is called nitrate. Nitrates have a really high desire to be dissolved. This compound is soluble by rule 2. And so we can see that functionally what happens is the calcium doesn't really have a strong preference. Chloride kind of wants to be dissolved. So that compound dissolves, those ions separate out, float around in solution. Chloride kind of wants to be dissolved, but silver, as rule 3, higher priority rule, really does not want to dissolve. So silver and chloride stay dissolved. They do not separate out into stay undissolved. They do not separate out into individual ions. They do not become aqueous. So, if you had solid silver chloride, it just doesn't become aqueous. So, if we were to write out what that means is if we were to write out, like silver chloride solid dissolves in water, there's just nothing that happens. We make silver chloride solid, which isn't a process. It just doesn't change. And so, in your beaker, it would just look like, you have your beaker, you have your liquid, and there would just be, you add it in, and there would just be a little pile of silver chloride. It does not dissolve, it just stays solid. So it doesn't separate out into ions, they don't float around, because these silver cations really don't want to be dissolved in water. They don't want to be floating around. If you pair something like nitrate, nitrate really wants to dissolve. So that's silver and nitrate. That nitrate has a stronger desire to dissolve, hence higher priority on the rule. And that's how you can get silver and nitrate to both dissolve, float around out in the solution. Question 1 for participation 219. Determine whether each of the following ionic compounds is soluble in water. First, I have LiF, that's lithium fluoride, then Al2CO33, that's aluminum carbonate, BaSO4 is barium sulfate, and NH4NO3 is ammonium nitrate. So for this first question, I have these 4 compounds. I would like to know whether or not each of them is soluble or insoluble in water. You just need to tell me soluble or insoluble. That's all I'm looking for on the answers there. Again, that's question 1 for participation 219, due Friday, February 19th at 11:55 p.m. on Blackboard. Determine whether each of the following compounds is soluble in water. LiF is lithium fluoride. Al2CO33 is aluminum carbonate. BaSO4, barium sulfate, NH4NO3, ammonium nitrate. All right. Participation 219 is what we just saw our first question for. We're looking for questions for that. It's going to be due on Friday. Got a couple more videos. See if we find some more questions. See you there.